This is the first lecture about waves. Waves are everywhere. Light waves, sound waves, waves produced when an earthquake happens, and then those waves reach the surface of the earth and cause destruction. Waves can be understood mathematically, and I'd say only mathematically. So the goal of this lecture will be to derive what is known as the wave equation. It will be a partial differential equation, but don't be afraid. I will explain what partial derivatives are for those who don't know them. I'm also going to be using an animation that was produced by the University of Colorado. And it's a brilliantly done animation. I'll encourage you to play with it because there are lots of features, and we'll be using this as a kind of template to understand various properties of waves. Okay, so let's get on with it. Let's first take a quick look at the applet or the animation. So let's look at this button. I'm using the pulse mode. We'll go to the others later. That means that this piston over here will go up and down and create a pulse. The amplitude of the pulse or the size of the pulse is adjustable. Presently it's 0.4 centimeters. We can use a ruler and let's see now, or a reference line, which would be better. And I can move that reference line so that it can be made to adjust the size of the pulse. And so let's make it 0.4. Now I'm going to click on this button and you see a pulse travels down and its size is 0.4 centimeters. Well, I can increase that. Let's make it, 0.6 centimeters. So it should be somewhere here. Let's send that pulse down now. And indeed, this is a pulse that is traveling down with 0.6 centimeters amplitude. I can adjust the pulse width. So let's make it now 0.6 also. And that means it's going to be a wider pulse. Now notice over here that I have selected no damping. No damping means that this wave continues on without any loss of height. And if I increase the damping, so if I make it like this, then you will see that it becomes smaller in size and eventually becomes very, very small. Now I'm using here an infinite string or a rope which has no end. Later on we will be using these options as well, loose end and fixed end. The tension presently is low. What this means is the following, so let me use slow motion now. Here you see that as it goes along, there's a force that's pulling it down. Let me remove the tension, the damping, and do it again. So why does this string want to come down to its normal position? The reason is that there is a force which is pulling it down. That force comes from the tension. Now, what would happen if I was to change that tension and move it from low to middle? Well, let me send a pulse again. So now you see that the pulse is moving faster. And if instead of slow motion I use normal speed, then let's see how that works. You see the pulse is traveling faster. So clearly the speed of the wave has something to do with the tension. When it's low, then the pulse travels slower. When it's high or higher, it'll travel faster. And if I increase this still further, then it'll travel still faster. In fact, let me decrease the pulse width and do it again. So you see it's traveling very fast. Now, instead of sending pulses, I can make it oscillate as well. So here is the piston moving regularly up and down. I can change the frequency. So let me decrease the frequency a bit. And you see that I have changed the frequency, but I've also changed the wavelength. That is to say, the distance over which it repeats itself. Let me go the other way now. And you see that the frequency is increasing and the wavelength is decreasing. Again, as I say, we are using zero damping. We can adjust the amplitude. The amplitude is the height, and we can make it smaller, or we can make it larger at will. Okay, now let's try and understand traveling waves mathematically. So imagine that this is a wave that at some earlier time looks like this. Let's call that time t equal to 0, which after 1 second moves here, and after 2 seconds is here, and keeps traveling the way you saw in the animation. So it's going this way. Now, in principle, this could be any shape, but let's take a very simple one. So I'm going to take a function. Consider a function of, let's say, this variable z, which is an exponential, actually something that is called a Gaussian, so e to the minus z squared. Now you know that as the argument of the exponential increases, the function decreases very rapidly, and that when z is equal to 0, the function is 1. And so this plotted out looks like this. It's maximum, that is 1 over here, and then it is 0 on this side and 0 on this side. And if I was to take a computer and plot it out properly, it would look like this. Okay, now this shape is actually moving like this. So now consider the function f, which is now a function of x and t, and it's e to the minus x minus vt squared. So instead of z, I've put x minus vt. Z is x minus vt. Now just digest this. When x is equal to vt, z is equal to 0, which means that the function will be e to the minus 0, that is to say 1, when x is equal to vt. So at x equal to vt, this function will carry its peak. So here, when x was 0 and t was 0, it had its peak. But now that peak is here because t is 1, so x is v. Here x is 2v, and so forth. Now there's another way of looking at this. Suppose x changes to x plus dx, and t changes to t plus dt. Then you see from here that dz is equal to dx minus v dt. However, if you're moving with the wave, that means you're at constant z, so that z could be the peak, in which case it would be 0 over here. That means that 0 would be dx minus v dt. And that says that v is dx by dt. So this is the speed at which the wave is moving towards the right. In other words, let me repeat this, in order to keep this argument constant, in other words, dz equal to 0, z is constant, means dz is 0, then you have to move this way at this speed in order to be at the peak of the wave at any given time. Now, more generally, if there is a function, any function of x minus vt, and you want to keep this over here, z, equal to constant, that is to say, if you want to move with the wave, then dz is 0, and then we get back to this condition over here. But now, think of the fact that this function over here appears to be a function of both x and t. But in effect, it is a function of only one variable, z. In order to get to the wave equation, which I promised you, we will have to understand a little bit of partial derivatives. And so that will be our next challenge. Okay. To understand partial derivatives, let's go back to the calculus that you learnt in school. So suppose that I have a function of x. And now, what if I look at this function at a slightly different point? So delta x is supposed to be small. I subtract it from the value of the function at the original point, divide by delta x, then this is what I call, or what is called, delta f by delta x. That is to say, how much the function has changed when you changed x by a little bit. And of course, if I take the limit as delta x goes to 0, then this becomes the definition of the derivative df by dx. Now note here that this was a function just of one variable, x. You changed x a little bit, subtracted it from its old value, and you got the derivative in the limit where this delta x becomes very, very small. And so you could write this as the change in f is the derivative df by dx into how much x has changed. Okay, so that is going to be how we're going to define partial derivatives as well. So now consider a function which is not a function of just one variable, but of two variables, or maybe 3, 4, 5, 6 variables. There's no limit to that. Now the question is, what happens when I change x by a little bit, but I do not change y? So I'm only changing x, keeping y constant. Well, in that case, what would you expect? That the change in the function will be the derivative by how much multiplied by how much you have changed x. But now we don't call this df by dx, we write it as curly f by curly x. And that's called the partial derivative of f with respect to x, keeping y constant, and if there's z or w or any other variable, you hold those constant as well. And so it is this. So it's just exactly the same as this. So this was with y constant. Well, what happens if I don't change x but I change y? In that case, what would you expect? Well, that the change in f will be df by dy. See, I'm calling this df by dy, although I should really call it partial f by partial y. And but we just save words this way. What's the difference between this and this? Well, here I have kept x constant instead of y. All right. Now you can ask yourself, what will happen if I not only change x, but I also change y? In that case, the change in the function, let's call that df, will be simply the sum of the changes. So it will be df by dx plus df by dy dy. And of course, if there are other variables, if there's z and w and so forth, then there'll be additional terms over here. Now let's work out an example. So suppose we take a particular function. Suppose I take f of x, let me manufacture something, let's say x cubed y plus 3x. All right. In that case, df by dx will be how much? Well, I'm holding y constant and I'm only differentiating with respect to x, so that will be 3x squared y. And then, of course, I have to add on this term too, so I'm differentiating 3x with respect to x, so that's plus 3, just 3. And what about y? Well, if I was to differentiate this with respect to y, then I hold x constant and I simply differentiate with respect to y and I get x cubed. And of course, this is independent of y, so I don't get anything from there. Now let's look at a very particular function, f, which is a function of x and t. And here, this f is a function of x and t, but it's actually a very particular function. It's a function of this quantity x minus vt, where we had, you remember, called x minus vt z. Okay, so I now want to take the derivative of f with respect to x. Why I want to do it, you'll see in a little bit. But I first want to differentiate with respect to x, and then I want to differentiate with respect to t. But let's start with this. So, since f is a function of z, then by the chain rule of calculus, that's the same as this. And now dz by dx, that's a quantity that you can see from here. Here dz by dx is just 1. Okay, so this is the same as df by dz. That's easy enough. What if I want to take a second derivative? So I want to take d by dx of this thing again, df by dx. That's what we'll call, that's by definition what we call d2f by dx squared. It's just a different way of writing this. Well, how do we calculate it? We do it as we did before, d by dx of z, d by dz of now df by dx. But you see, dz by dx is 1, so this over here is 1, and this is d by dz of df by dz, and that's what we've agreed to call as d2f by dz squared. So it's a pretty trivial thing to see that d2f by dx squared is the same as d2f by dz squared. Let me still write it down over here. So d2f by dx squared is the same as d2f by dz squared. Fine. But now I want to repeat this whole exercise and not differentiate with respect to x, but differentiate with respect to the time t. So let me do that. I'll do df by dt, and that's dz by dt, and then how f changes with respect to z. And now dz by dt, you see from here, dz by dt is not 1, it's minus v. So this gives me minus v df by dz. Fine. Then let me take a second derivative. And again, you'll see why I want to do that. So d by dt of df by dt, that's the same as d2f as I wrote over here. The only difference here is that this is d2f by dt squared. And now to calculate this, so you see this d by dt of z, d by dz of df by dt, and this is minus v from here, and we've already calculated this d by dz of df by dt, and that was minus v into d by dz of df by dz. So that's d2f by dz squared. And so to summarize these steps over here, what we found is that d2f by dt squared is equal to v squared d2f by dz squared. So look, these two are almost the same, and if I was to just divide this by 1 over v squared, I'd have 1 over v squared d2f by dt squared is equal to d2f by dz squared. So you see, on this side and on this side, we have the same thing. What that says is that d2f by dx squared is the same as 1 over v squared d2f by dt squared. And that is the wave equation. That's the wave equation. You see, another way of writing this would be, you could say d2f by dx squared minus 1 over v squared d2f dt squared is 0, but this is perfect. Now, this equation describes all kinds of waves. So your function could look like this, as we had made it look earlier, but it could also look something very complicated like this. All these functions are moving towards the right, and that was on the assumption that this function could be written as a function of x minus vt. Well, what if it had been x plus vt? So I'm running out of space. Over here, suppose I had a function, let's say another function, which was a function of x plus vt. Well, if x minus vt is running this way, so if f is running this way, g is running the other way. In order to hold this thing constant, then x must decrease. Here, x must increase with time. You have to run with the wave in this direction. Here you have to run in the opposite way. So anyway, here is the wave equation, and we'll come back to this. As the last thing we're going to do, let's return to periodic waves. So consider a function of x and t, and let's make this the function sine of kx minus omega t. Okay, now we can, of course, write this in the following way. We can write this as sine of k into x minus omega by k t. And you see, this is of that form, x minus something times t. And so automatically you know that this is going to be a solution of the wave equation. Remember, the wave equation says that anything which has the form x minus function of x minus vt is a solution of the wave equation. And so obviously this is a solution of the wave equation, and this omega over k is going to be the velocity of that wave v. In fact, there's a word for it. This v equals omega over k is called the phase velocity. Now, this phase velocity is simply the frequency divided by the number, the wave number, it's called k. But before we end, I just want to remind you of the meaning of k and omega. So let's spend the last few minutes doing that. Okay, so what we're looking for is the meaning of omega and k. And remember that the phase velocity is simply omega divided by k. All right, let's take a fixed time t. So we're going to fix this. If you like, we can fix it at 24.5, but it might be nicer if we simply fix it at t equal to 0. It doesn't make any difference. Then we have this function of x only, sine of kx. Well, you know that when kx is 0, then the sine is 0. When kx is 2 pi, then again sine is 0. And that sine repeats itself. So never forget this graph. That sine starts from 0, goes up, comes down, goes up. And this over here, this separation in x's is what one calls the wavelength. Lambda is this. Or you could say lambda is the distance between this point and this point. Maybe it's nicer to say it's the difference between the peaks, but basically the point is that the sine repeats itself after 2 pi. So when kx becomes 2 pi, the wave repeats itself. When it's 4 pi, 6 pi, 8 pi, or any integer times pi, then the wave comes back to its original value. Now, for that, so this x over here is the distance over which it repeats itself, and that means that k lambda is 2 pi over k, and that gives us the meaning of k. The meaning of k is, it is basically 1 over the wavelength. And that's why this is called the wave number. It sort of counts the number of waves. So lambda, which is the distance between these 2 points, or between this point and this point, or between this point and the next time that the sine becomes 1, that is the wavelength. So obviously the dimensions of k are 1 over the wavelength, 1 over length. So we write this as dimension of k is 1 over the length, L minus 1. Now, what's the meaning of omega? All right, so let's fix the position x. And we could take any position, but you could take position just x equal to 0. It's more convenient, but you fix x and then you ask, after how long, after how much time does sine of omega t repeat itself? So you see, the sine as a function, so here there was x on this axis, now there's t on this axis, and the function sine of omega t, it starts from 0, goes up, comes down, and then goes up again. The time it takes to come back to the original value, so that could be this time, the time that separates this peak from that peak, that is what we call the time period. And so just like as over here, after a certain time t, omega into t will be 2 pi or 4 pi or 6 pi or whatever. And so the meaning of omega is that it is 1 over the time. Well, 2 pi over the time. That's why this over here is sometimes called the angular frequency. It's some people like to call it frequency, but you can also call it angular frequency, whatever. So basically, when you have a periodic wave, and look, it doesn't matter whether this is sine or cosine, every trigonometric function, sine or cosine, it repeats itself. And this is how, as I've shown you, we define omega and k. Omega is 1 over the time period, k is 1 over the wavelength. And now, again, I remind you that this is what is called the phase velocity. That's the velocity with which this wave is moving to the right.